Hey guys, welcome back to the next part of the neural networks tutorial. So in a previous part I just explained the overview of how a neural network works, and I explained its basic functionality and also the basic ways to implement it. But in the next coming parts I'm going to be implementing it in JavaScript and also going to be talking a lot more in depth about the different areas. So let me just open Clicky Paint tool again, and I'm going to illustrate which part of a neural network we're going to be making today. So in today's video, all I'm going to be doing is making the main network itself. We're not implementing any sort of persistence, learning algorithms, nothing like that. All I'm going to be doing is making a raw network. So what I mean by that is, if you remember from the previous video, if I use these circles to represent nodes and use these, so as you can see, there's a bunch of layers, and basically a layer is just a section. Like, for example, this is a layer, this is a layer, and this is a layer, like that. And we'll know that these neurons are connected to every neuron in the next layer, like this. And then these are connected to every single neuron in the next layer, just like this. And yeah, so we're going to be creating something like this. We pass in things. This is our input layer, so let's say you pass in like a 0.53, and we're expecting a certain output, for example 10, and these are all weights. We have biases as well, but we'll talk more about that in the video itself. So here I've created a new folder for this project, and what I'm going to do is I'm just going to create a project template. So I actually have my own template thing. We're going to be using TypeScript, which is basically the same as JavaScript. So if you're just using JavaScript, then you should be fine. But yeah, I've created a little npm package which basically creates a vanilla TypeScript template for you. And if we select this, now you can see we get all of our things. It comes with its build thing. So I'll talk more about this later. But for now, what's important is that we just have our source folder and we have our index.html. So let's just call this neural network, and we're not actually going to be doing anything related to HTML, so I can refresh this and go into source, and yeah, basically we're going to be working almost exclusively from the terminal here. So yeah, I'm going to make this a little bigger so you guys can see it. But yeah, so we're going to be recreating this, and let me go over to here, close this, and we'll start the TypeScript compilation. So let's just test if this is working. Go here, and yeah, this is looking good. Let's just change this, just like that, and we might have to refresh, but yeah, okay, that's working. So I'm going to be using an object-oriented approach, and the first thing I'm going to do is we're going to create multiple classes. So I'm going to have a class for a layer, I'm going to have a class for a neuron, and we can also have a network class, although this one may not be as important. So in the network I'm going to have a list of layers, which we can just do layer like so, and in the layers I'm going to have a list of neurons just like this. And when we initialize our thing, we don't really want anything to happen, so we can kind of just leave this blank for now, of course. Okay. One thing we also need to do is give these their properties. So we know a layer has neurons, but a neuron's going to have its value, which is going to be a number, and we'll just initialize this to 0 by default. And it's also going to have its raw value, which will be used later. Not too important, so just keep in mind that there's a raw value and a value. Basically the difference is this has activation. Basically it's just the activation function applied to the raw value, just like that. And then this is the value which gets passed on to the next one. And finally, a neuron also has a weight or multiple weights and bias, single bias. Each neuron, if you remember from the previous video, this could have a something like, let me do this in white, this could have like a +1, this could have a -2, so each neuron has individual bias so that it can stop being directly proportional to whatever it's got. And then yeah, I'm also going to have to create a few functions, so let's just create a base activation function. This is going to be a static activation function, takes in a number, and this is going to return a we have a few choices here, but what I'm going to return is the tan h, because hyperbolic tan, because this is very similar to a sigmoid curve. Basically all it is if this is the xy plane, it's going to look something like that, you know, like it's just introducing non-linearity into our thing. So yeah, actually while we're making that, I guess it might be easier if we just return a simple linear thing. So here literally all I'm doing is that, or it might not even be that. I feel if it's just constant, right? Actually no, yeah, this is just this is just this graph. So yeah, if you imagine this is what our activation function is right now, just completely linear. So we can change that once we've finished building the rest of the network. So now we have basically all the building blocks. We can actually start. What I'm going to do is, if we go here, I'm going to create a network object. Let's just call this network, and this is going to be new network, like so. And we want to give it some layers, so network.layers is equal to this, and we're going to create a few layers. So let's have an input layer, and let's create a new layer, and we can actually add something in the constructor. We can say num neurons, this is a number, and it's just going to add a new neuron for each one. So this dot neurons is equal to blank, and we're going to add the number of neurons which is specified into this. So let's just do for let I equals 0 is not equal to num neurons, this dot neurons dot push new neuron, just like that. So it's a bit cleaner when we do this. So as you can see, our input layer has 2 neurons, our hidden layer, this is the middle layer is called the hidden layer because you're not actually going to see it. All you're looking at is the input layer and the output layer, and you can have as many of these hidden layers as you want, but for simplicity I only chose one. But yeah, that has 3 neurons, and then we have an output layer equals new layer, and this has 2 again. So now I can set the network.layers to this input layer, hidden layer, and output layer in that order as well. So once we've done that, this is basically our network object. Let's just console.log this to see what it's looking like so far, and we can have something like this. And why is this taking so long? Has it crashed? I'm actually not too sure. Let me retry. Oh, okay. Guess not. Yeah, so we can look at our network and see it's just literally just a list of layers. So now what we're going to do is we're going to want to input some put some numbers into this. So for example, if we were going to input the 0.53, what we would do is we do input layer dot neurons, and we can say neuron 0, which is representative of the first one. Let's set that to 5. Oh, neuron 0 dot raw value, of course, and we want to set the value of this neuron 1, we want to set its raw value to 3, like so. And yeah, so now what we want to do is we actually want to run the neuron through this and get the numbers like so. To do so, what I'm going to do is I'm going to create a run neuron function in the run network function in the network layer network class, and let's call this run network. So this is going to assume you've already inputted the raw values of the points which you want in the input layer. Now the first thing it's going to do is it's literally just going to go through, and it's going to go through each layer. So we want to get groups of layers. So for example, we're going through these two first, so you can calculate the things of all of these and then put those in there, and then we'd go in groups with these two to calculate the ones of this. So to do that, what I can do is I can actually create a for loop for let I is equal to 0, I is not equal to this dot layers dot length minus 1. I'm going to put that in brackets just so it's a bit clearer, and then let's just do I plus equals 1. So we have const current layer and next layer. Yep, so current layer of course represents this, and next layer represents this in the pair which it's going in. Now what we're going to do is to calculate the value of this one, we want to take the value from this previous one, multiply by this weight, then we also want to take the value from this one, multiply by this weight, and that will tell you, add them together and it'll get you that value. So you might be noticing we actually need some weights, and obviously what I can do is I can just create a brand new, not class, but it's going to be a dictionary. I'm going to indicate that it's like important or global using the using fully uppercase, and yeah, let's just show its type. So to represent a weight is literally between two neurons, so I can give each neuron an ID and I can initialize some weights. So let's say ID string, and we can have something like this. So we want the key, this is going to be a string, and then this is going to actually be a number, and yeah, because remember weight is just a multiple. So we've done this, and let's just tell it what the key is actually going to be. It's going to be a JSON.stringify of the neuron1.id and neuron2.id. And we'll also have to give these neurons individual IDs, which should be pretty simple because we can just assign that ID to a random number. So when a neuron is created, we're also going to give it an ID, and if we do this in the constructor, we can do something like, what's wrong with this? Oh, sorry, that's what's wrong with that. Yeah, so what we can do is we can give it a constructor, and we can just say constructor this.id is equal to string, and then we'll just say math.random. This is our random ID which we're assigned to every neuron. So now we might want to initialize our weights whenever we have the chance, and I'm actually going to leave that there. I'm going to initialize random weights for now, but in the future they won't be random, they'll be persisted through many iterations. So we'll go for, I'm actually just going to take this code, actually we can put this inside the network class, so we can have a new function. It's going to initialize weights, and in fact I could actually move this in here, which is very easy. Okay, so what I'm going to do is I'm literally just going to go through each layer individually, and we have the current layer and the next layer, and then for each we're going to have to loop through each neuron in the current layer. So for const neuron of current layer dot neurons, we're going to have to loop through every neuron of this layer as well. Neuron 1, neuron 2, next layer. And yeah, this video is actually going to be quite long because this is mainly the bulk of the thing, because it's mainly setting up the groundwork so that in the future I can create easier videos which are easier to understand, because we already have this done, which is just creating the network itself. So what we're doing here is looping through every single neuron between these two and then between these two, so we can get the individual weights between each neuron. So let's create const key equals JSON.stringify, and you can see I can literally just copy this in just like that. Now we have our key, this dot weights key, and at first I'm just going to initialize it as 0, but in the future that is going to be a random number. Initialize. Okay, so now we can actually start. Sorry, this is taking quite a while. Network.initialize weights, and let's just console.log our network to see what it looks like. So if we go to here, we can see our network has the layers, and it also has wait, oh, what is this? Let's see what I'm doing wrong here. We have, okay, this seems like something is happening. Oh, I think I know what I've done wrong. If I go to active neuron, yeah, I forgot to actually call this function. Alright, now let's go back, go to weights, and you should see that there's a weight between every single neuron in this, and we can confirm that by going to this layer. You can see the first neuron has this ID, and if we go to try and find that ID, you can see that has 2 weights coming out of it. So what that represents is, actually there should be 3 if I'm not, oh yeah, there are 3, okay, yeah. So there's 3, what that represents are the 3 weights which come out of this neuron. So now what we can do is we have our weights, we have our biases. Actually, we don't have our biases, we'll add that in later, but yeah, so we have our weights, and now we can actually run this. So I'm actually going to copy this code like this, just because it's a similar action. We have to go through every neuron, except the difference is now we have to loop through the other way around, like this. So we'll start on this, and we're getting every value here, and we'll create a sum, which is going to be a sum of all of these values multiplied by their weights. I'm also going to set these neurons, we're just going to set their value rather than raw value, just because you don't usually activate the inputs, and set initialize sum as 0, loop through all these, and we'll find once result, which is going to be the neuron 1 dot value multiplied by the weight which corresponds between these two. Weight equals this dot weights JSON dot stringify neuron 1 dot ID and neuron 2 dot ID. So now we can multiply that by the weight, then add that to the sum. Here, sum plus equals result. Okay, finally what I can do is I can set this neuron2.raw value to the sum, and then usually would add bias here, but I'll do that later. Actually would add bias to the sum like so, but I'll do that later, and then we pass it through the activation. So neuron.activation function of the raw value, which is neuron2.raw value. Okay, so I hope that makes sense. Now we should just propagate through everything. If we run this, we should actually get a result. Obviously it's all going to be 0 because we initialized the weights as 0, but let's just see what we sort of get. So we could console.log the network before and after. Actually, we're going to have to pass it. Stringify. Do it before and after, like so. Okay. So before, this is what our network looked like. The first layer had, just to make it a bit smaller. Yeah, so the first layer had these neurons, which have values 5 and 3, which is what we assigned here. And then if we look at the other neurons, of course they don't have anything because nothing's happened to them yet. So we'll close that, and then this is the after. So the first neurons still have the value 5 and 3, but then if we go here, these all have 0, 0, 0, and 0, 0. The reason for that is because we initialize the weights as 0. I'll actually make it 1 so we can understand it a bit better. So if we look at the weights now, they're all 1, and of course these are still going to have 5, 3 like that, because of course nothing happens to them. If we look at the neurons in the second layer, now they all have 8, because if you imagine 5, 3, these weights are all 1, so the value of this is going to be 5 multiplied by 1 plus 3 multiplied by 1, which is going to give you 8 in all of these. And then these are all 8, so we can actually calculate the value of this output neuron before we even look at it. So this is going to be 8 multiplied by 1 plus 8 multiplied by 1 plus 8 multiplied by 1. So the value of both of these output layers is actually going to be 24. And if we look at over here, that's exactly what we get. But let's actually, if we look at the value, it is 8, which is quite surprising actually, because oh yeah, that makes sense as well, because our activation function was just returning a num. Now I'll show you what the activation function does in reality. If we go here and we go here, so the first neurons still have these same things. Then second neurons, you can see their raw value is 8, but their actual value, the value which is going to be carried on, is 0.999. The reason for this is because this is what hyperbolic tan looks like. I think it's around 101 or 4 and 4, I could be mistaken. Either way, 8 is somewhere out, this value is 1 and this is -1, so the value of 8 is going to be very close to 1. This doesn't actually reach 1, but it's going to be very close to 1, which is why we get the corresponding value of 0.99. So yeah, that's one disadvantage of the tan function, and it's actually called the vanishing gradient, I believe, or it could be the exploding gradient problem. But yeah, it's quite a serious problem, which is why there's some other alternative activation functions. So yeah, you can see now, if we look at our output layer, if we go to our output layer, the value again is 0.99 and 0.99. So this is exactly what we're looking for. If we were to change these values to, let's say, 5 and 1, these would change slightly, not by much, but slightly. So if we go back, and yeah, you can see now they're different. That's actually quite a big change, probably because the 1 is now not being sent as far to limit of the hyperbolic tan function. But yeah, now the final thing we need to do before I end this video is add in the biases, and we can also add in a random weight function. So let's just create a static function over here, static random weight, and this is just going to return random number from -4 to 4, because I believe that's a recommended number, although that could be for the Sigmund curve. I'll actually just do it from -1 to 1, since that's a lot simpler. So to do that, it's pretty simple. I believe all I have to do is get 2 lots of a random number. So let's say something like math.random plus math.random, and this is going to give me a random number from 0 to 2, and now I can just offset that by 1, and now I'll just set that to this. Cool. Oh, because it's network.random weight, like so. Okay, let's look at our weights, and yeah, that does seem like a pretty even spread between -1 and 1. So now our network is actually going to be quite unpredictable. It's probably going to give us it is going to give us a different value every time. So here we've got 0.7 and 0.22. If we restart that, they're all going to have completely different weights. So now it has minus 0.035 and 0.45. So yeah, what we've done is we've basically given it random weights, and in future tutorials I'll implement persistence so that on each refresh they don't actually completely reset. They'll be saved in local storage, but this is about as much as I'm going to do for today. And the final thing to do before I end the video is add biases. So I can add those in a pretty similar way to how I added the weights. So we'll have biases, and the difference between biases and weights is that for a bias you don't actually need 2 neurons. The idea of 2 neurons, since it only applies to each individual neuron. So for the key, all I really need is the neuron's ID. String number equals For the sake of consistency though, I am actually going to use the same format I used for the weights, the only difference being it's not going to have two neurons, it's only going to have a single neuron, and we can have a function initialize biases like so, and we're just going to loop through every single layer, so for const layer of this dot layers and for const neuron of this dot neurons, layer dot neurons, we're going to have p equals neuron b, and the biases are always initialized as 0 no matter what, so that's not too much of a problem. You just have to do is equal to 0. The final thing I have to do is add the bias here, so we can just get the bias using const bias is equal to this dot biases, and let's have something like the key is going to be json.stringify of the second neuron, so neuron2.id, and we'll just add that onto the sum. Alright, there we go. Since they're all 0, it's really not going to affect it too much, and I also need to initialize it, obviously, like so. Okay, there we go. So we have our weights for each neuron, between each pair of neurons, and we also have our biases. You can see that these have individuals, so this is the weight between neuron ID 0.63 and 0.388, and you can see those are these two like that. So yeah, thanks for watching, and actually not yet. Let me just think about this. So we have 0.63. So what these two represent are the actual neurons in these two, and yeah. So I'm actually just going to show you a quick demonstration of what a bias can do. Let's look at what the output layer neurons are looking at right now. So they have a what is the problem here? Seems to be some kind of issue actually. If we go back. Yeah, the raw value is null for some reason. I'm not sure what's happened there. Hang on. This seems to be a problem. Console.log bias. Let's see. Okay, so again a bunch of undefines. That does seem to be the problem. I know what the problem is. We forgot to put this in an array, like so. Okay. Now let's look at the neurons. Yep, so these are our raw values, and now if I were to make all of these biases, let's just say something like 10, we should be expecting at least an increase of 10 because the last layer biases are going to get added. So let's see. Yep, the raw value goes up to 9, which makes the normal value go up to 0.99, close to that limit of 1. But yeah, this is the basic groundwork for our neural network. In the future tutorials, I'll implement things like persistence, storing the weights and biases over. That is the reason why I didn't include them in the network, but rather as a separate things, which makes them easy to store separately, as well as implementing some kind of learning algorithm for this kind of series, which is very basic. I might not go into back propagation, might stick with finite gradients and things, but we'll see. And then I might use it for a visual example, using points and classifying the points. But yeah, thanks for watching, and I'll see you guys in the future tutorial. Bye.